In this video, we're going to be working with the different operations that we can apply to complex numbers. What I wanted to do first is properly motivate the subject. So we've already learned from elementary and middle school that you can represent real numbers on a line. So any real number that you can think of could be represented as a point on what we call the real line. So that could be, you can think of any real number, so that could include decimals, like if you wanted to write 5 halves, which is 2.5, that would be right here, so it'd be a point in between 2 and 3. If you wanted to write pi is 3.1415926535, blah 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 blah, so that's very close to 3, so that would be a point, pretty close to 3. E is another constant, 2.7 blah 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 blah. That's a number that's a little bit more than half between 2 and 3, so that would be closer over here. Square root of 2, that would be somewhere over here. I'm sorry, on this side. So any real number you can think of, as eccentric as you want it to be. So, 7 divided by pi, that's a real number. Square root of pi, eighth root of pi, square root of 2 times pi. All of these are different, real numbers, and they can all be represented on the same line. So why am I talking about this, or what does this have to do with complex numbers? Well, complex numbers are numbers of the form a plus bi, where a and b are real numbers, and I represents the imaginary unit. So complex numbers can be represented on a plane. See, real numbers, you can represent them on a line, but to represent general complex numbers, you need to have a plane. And we call this the imaginary axis, and we call this other one the real axis. So, one thing to notice is the set of real numbers are on that plane. They are on the complex plane. Complex plane. So that tells us that real numbers are technically considered complex numbers. Remember, I said complex numbers are numbers of the form a plus bi. So if b is 0, then essentially you get all of the real numbers, because it would be like pi plus 0i. That's just pi, right? So all of the real numbers are indeed complex numbers, but not all complex numbers are real numbers. So complex numbers are more general than real numbers. So complex numbers, you can denote them on the plane. I'm going to go ahead and make these little tick marks, and these represent multiples of I. So the imaginary axis is just there to kind of tell us the multiples of I. And now you can represent any real number on the complex plane. So let's talk about, you can represent any complex number on the complex plane. Let's go ahead and talk about the number 2 plus 3i. So this is a complex number, 2 plus 3i. So you'd be plotting, if you wanted to see where this point was on the plane, essentially you're just plotting like XY coordinates, right? Like on the Cartesian coordinate system. So 2 represents the real along the real line, that's right here. And then 3 represents along the imaginary axis. So this would be 3, and we were at 2 and we did 3i. So that would be somewhere up here. So that point that I posted here represents the complex number 2 plus 3i. Okay, so this is my general introduction to complex numbers and their geometric interpretation. So this is what complex numbers look like geometrically. Of course, we're not going to be working with them geometrically in the class. You will when you take pre-calculus, and especially in calculus, it will be important if you do complex variables. Um, but as far as algebra 2 is concerned, we just want to kind of focus on the more simpler properties. So let's go ahead and talk about how you simplify the problems in the worksheet. So let's say I'm going to start off with number 4, since that one doesn't seem to have been worked out. So in number 4 we have negative 8i multiplied by 2 plus 7i plus 30i. Alright, so let's talk about what we're going to do here. Remember, again, going back to this, complex numbers are written in this form, a plus bi. So what we want to do is use our rules, our algebraic rules, to simplify the expression that we're given until it looks like this. We want to keep simplifying it down to the best of our ability until we finally get something that's of the form a plus bi. So let's kind of go back to this. We can start off by using the distributive property right here. And then we have negative 8i times 2 is negative 16i. So you simply just multiply the coefficients, and then you keep the I. Negative 8i times 7i is going to be negative 56i squared. That's important. So you're kind of treating this I like an x when you first learned how to do this. So I times I is I squared, and we'll talk about what happens with I squared. Alright, so then you bring down plus 30i. Okay. Now before I try and combine any like terms, let's deal with this I squared. So I, which we call the imaginary unit, is defined as the square root of negative 1. So what that means is that I squared would be I times I. That's what I squared is, right? I times I, which is the square root of negative 1 times the square root of negative 1. Now, when you multiply the square root of something by the square root of that same thing, you're going to get, guess what, that same thing. So this is just simply negative 1. Alright, so again, you don't have to do this because you're going to memorize the fact that I squared equals negative 1. But if you wanted to derive it, let's say you forgot, the square root of x times the square root of x is equal to x. This is the general rule that I use there to derive this. So we know that I squared is equal to negative 1. Whenever you see an I squared, you can replace it with negative 1. So let me copy this again, negative 16i. This turns into minus 56 times negative 1 plus 30i. Now we can simplify the resulting expression. Negative 56 times negative 1 is just 56. Negative 16i plus 30i is, what is that? That's 16 is, take away 6, so that would be 14. That's right. So we get plus 14i right here. And notice that this is in the proper format. Remember, our complex numbers are of the form a plus bi, where a comma b are elements of the real numbers. Okay. So once we simplify our expression down to this point, we know that it's already in complex number form, and we're basically good to go from there. Alright, so that was number 4. Let's do some more complicated ones. Let's try 5. So in question 5, we have 2i times 7 plus 3i, and then parentheses plus 5 times negative 5i. Okay, we can go ahead and distribute. So 2i times 7 is 14i, 2i times 3i is 6, so plus 6i squared, and then plus 5 times negative 5i is negative 25i. So we're going to do the same thing. When we see an I squared, we know that we need to replace that with a negative 1. So I'm going to go ahead and do that here. And that is just negative 6. Then you can combine these expressions that have I in them. So 14I plus negative 25I is going to be negative 11I. So you get minus 11I. Alright, and then that would be our answer. Now remember when I had mentioned that complex numbers are of the form a plus bi? You might be looking at that and thinking it looks kind of strange. You might be looking at this and say, where's the plus sign? Like, why is there no, if there's no plus sign, does that mean it's not in standard form? No, that would be incorrect. And let's talk about why. Because a and b can be any real numbers. So that's important. So our a in this expression is negative 6. Negative 6 indeed is a real number, so it meets the criteria. And then the coefficient of our I is negative 11. So if you think about it, it's kind of like saying negative 6 plus negative 11I. So there's like a sneaky plus sign there. You're not seeing it, but there is a plus sign there. So our b is negative 11, which is, remember, b is the number in front of the I. Alright, so just because there's no plus sign here, that doesn't mean that we have written something wrong. It just means that our b is negative, which is fine because b could be any real number. And if you remember, real numbers include, sorry, my phone was acting kind of weird, but real numbers include negative numbers as well. Hang on. What's going on here? Okay. Alright, so the next one, so that was 5, let's see, 6. So in 6 we have 3 times 5 minus 4I minus 15, whoops, it's like that, minus 7I. Okay. So again, we're going to start off the same way. We just use the distributive property. 3 times 5 is 15, minus 12i. Is distributive property on this side, that's minus 15 plus 7i. Simplify resulting terms. Notice the 15 and the negative 15 cancel. Negative 12i plus 7i is going to be negative 5i. Okay, and that would be our answer. Again, you might bring up this objection. Doesn't look like it's in the form a plus bi, so how is it a complex number in proper form? Well, again, our a and our b can be any real number. In this particular case, our a is 0, so it's like saying 0 plus negative 5i. Right, so that's it's in proper form. Now, there's something interesting about this. I'm going to go ahead and write it in a red pen. Whenever you get a complex number that just has the bi, like the negative 5i or like 20i, there's a special name for these numbers. These are called pure imaginary numbers. It's kind of like a separate name for these. You might not use that in class, but just in case you see, if the teacher mentions something about pure imaginary numbers, it's talking about numbers that only have the imaginary component, as opposed to a real and an imaginary component. Alright, so numbers that only have that I without the plus or minus, other number are just simply called pure imaginary. Alright, so that's number 6. So I want to start getting to the trickier ones. So let's see. 7 has the FOIL, so we have to use FOIL in 7. 1 minus 4i times 3 minus 3i. Okay. So that means you have to distribute like this. So 1 times 3 is 3. And then 1 times negative 3 is negative 3i. Negative 4 times 3 is minus 12i. And then negative 4 times negative 3i. So this turns into positive 12i squared. Alright, cool. So what we need to do is simplify the resulting expression. So we have that I squared is over here in the back. We need to rewrite this using 1. A negative 1, I'm sorry. minus 12i plus 12 times negative 1. Okay, so now we can simplify. We have 3 plus, and this is 12 times negative 1. So this is really negative 12. And we're adding it to 3. So that's going to give us negative 9. And then negative 3 minus 12i. We combine those and we get minus 15i. And then at that point you'd be done. Let's get that one, that's 7. And then 8 is fun. Let's go ahead and look at 8. So in question 8, we have, I'm going to switch the pen actually, sorry. Need this. Okay. So for question 8, we have 1 minus 5i squared, and then minus 8 minus 4i. Alright, so the first thing we should do is go ahead and kind of expand this out. Whenever you see this squared with a binomial, you can rewrite it like this. I'll go ahead and bring down this other part over here. Now this turns into the same steps that we had followed in question 7. So we're just going to use the distributive property again. So 1 times 1 is 1. 1 times negative 5i is negative 5i. Negative 5i times 1 is negative 5i. And negative 5i times negative 5i is positive 25i squared. I'll go ahead and bring down the rest as well over here. Okay. So remember that 25i squared becomes 25 times negative 1, which is negative 25. And 1 minus 25 is negative 24. Okay. And then negative 5i minus 5i is negative 10i. And then on this side, we can go ahead and just distribute this negative sign there. So that's going to give us minus 8 plus 4i. Alright, cool. Now we can go ahead and combine like terms again. So negative 24 and negative 8 gives us what was that? Negative 32. And then negative 10i plus 4i is negative 6i. And then you'd be done at this point. So there you go. So that's question 8. Let me go over here for further questions. So 9, let's go ahead and do it. I'm going to split this so it doesn't look, it looks kind of messy like this. So I'm just going to do that. Okay. So for question 9, you have to be careful with this one because now we're working with division. So we have 10 minus 2i over I. So when this happens, you want to, it's probably a good idea to go ahead and break this into 2 parts. So this is like saying 10 divided by I, and then minus 2I over I. So again, all I did was I just used a rule from fractions that you can split this into 2 fractions. When you have a binomial over a denominator, the denominator would stay in both of them, and you would write the corresponding numerators. So we had a 10 there and a negative 2 from this over here. So you can always split fractions like that. So now that we've done that, things start to simplify. So this I over I cancels. So we're left with 10 over I minus 2. So things are looking good so far. We don't want this I in the denominator. You see how there's an I here? There's 10 divided by I. So what we're going to do is we're going to multiply just this fraction by I over I so that we can get rid of the I that's in the denominator. So I'm going to go ahead and write the resulting expression over here. Now we have 10I divided by I squared minus 2. Again, where did this come from? So we don't like having the I in the denominator, so we need to multiply by I over I so that I in the denominator, I times I, turns into I squared, which turns into negative 1. So effectively eliminating the I from the denominator. So that's how we're going to simplify this. So we have 10I over I squared. Remember that I squared, this guy is just negative 1. So this turns into negative 10I minus 2. Again, because 10I divided by negative 1 is just negative 10I. And then you can rewrite this, it looks like in that standard form, right, where you have the a in front and then the bi, right? So minus 10I, and then it would be like that. All right, so that's how you work with complex numbers that involve division. So 10. And 10 has a very important concept that you have to master in 10. Okay. So for question 10, we have 5I over negative 3 plus 2I. So the problem with 10 is we can't simply break the fraction the way we did in the previous question. See how we broke the fraction in the previous question? Here, it won't simplify our lives. It'll actually make it worse. So if you have a binomial or some other kind of polynomial in the denominator, that's not the best, approach to take. So what we actually have to do here, and I'm going to use a red pen so it stands out, is we're going to be multiplying by something called the complex conjugate. Okay, so let's talk about what this is. First, let me write the multiplication. So I'm going to write it like this. Times, okay. Now, the complex conjugate is going to be the same exact binomial, except you're going to flip that sign. So if there's a plus sign there, it turns into a negative sign. If there was a minus sign there, it turns into a plus sign. So we're going to be multiplying by something called the complex conjugate, like this. Okay, and I'm going to write it in red here. So that's the proper name for this, complex conjugate. It's kind of very important algebraic expression that you can construct. So why is this the, oh, I'm sorry, I didn't put a minus sign. I just realized that there should have been a minus sign. Remember, it's flipped, right? This is a plus, so it turns into a minus sign. Okay. So why are we using the complex conjugate? What does this do? Well, let's go ahead and multiply these out and see what happens. So I'm going to go ahead and write it like this. So I have on the top 5 plus I times negative 3 minus 2I over negative 3 plus 2I times negative 3 minus 2I. Alright, so I just kind of compactly organized it like that, and then we can go ahead and continue, simplifying this. So if you're looking at the denominator, we can multiply this the way we would multiply using the FOIL method. So I'm going to go ahead and copy this over here. 5 plus I. And we're going to have to do it to both the top and the bottom, but I'm just going to focus on the bottom for now so you can see what's going to happen. So negative 3 times negative 3 is 9. Negative 3 times negative 2I is positive 6I. And then we do 2I times negative 3, which is negative 6I. And then 2I times negative 2, which is minus 4I squared. So let's go ahead and kind of rewrite this. Negative 3 minus 2I. Okay. So what effectively happens here is the two terms in the middle are going to cancel. You're always going to get, if you're and this, by the way, this is true for any set of conjugates. Whenever you multiply a binomial, a complex number by its complex conjugate, the middle terms will always cancel out. So positive 6I and negative 6I becomes 0, so it goes away. And then you have a 9 here and negative 4I squared. I squared we know is negative 1. So negative 4 times negative 1 is positive 4. And then we add it to 9, which is going to give us 13. So notice we got rid of that complex, we got rid of the I in the denominator by multiplying with a complex conjugate. So we were able to get rid of that. Remember, we said we didn't want an I in the denominator. Alright, so now that we've done that, we can go ahead and continue simplifying. Now we'll do the same thing in the numerator. However, it won't nicely, cancel out the way it did in the denominator. So we'll see what we get right now. So 5 times negative 3 is negative 15. 5 times negative 2i is negative 10i. I times negative 3 is negative 3i. And I times negative 2 is negative 2i squared over 13. Okay, so now we can go ahead and start simplifying stuff. So we know that I squared is negative 1 times negative 2 is 2 plus, we're adding it to this number here, negative 15. So 2 plus negative 15 is just negative 13. Okay, and then this negative 10i minus 3i is going to give us negative 13i. Oh, cool. Look at this. The denominator is just 13. So whenever you see this, you can always, like, if you have a multiple, you have a number here, you have a number here, and a number here, and you can divide them all by the same thing and get whole numbers, then you're allowed to do that, if you can, if that situation occurs. In this case, we could divide all three by 13. So we end up with negative 1 minus I, and I was going to say over 1, but you don't have to write it like that. You can just negative 1 minus I. So it's effectively we just divided by 13. We simplify using 13. Another way of seeing this, if that looks strange, or you feel uncomfortable with that, you can always break the fraction the way we did this, I think it was number 9, the way we did this one. You can break the fraction like this as negative 13 over 13 minus 13i over 13. And then from here, you can immediately see how things simplify, right? Negative 13 over 13 is just negative 1. And negative 13i over 13, that cancels to negative I. So you see how you get the same exact result. So I just showed you kind of like the little shortcut that you can use. But if you want to be systematic and write it out this way, that's totally fine. Alright, so we got that. That one was, what number was that? Number 10. Where was that? That was number 10, right? Yes, that was number 10. Alright, so I'll let you practice the last two, 11 and 12, on your own. I'll give you a hint. For number 11, you'll be using the complex conjugate just like number 10. And for 12, you'll also be using the complex conjugate just like number 10. So for both of these, you'll be using the complex conjugate. Don't let 12 confuse you. 12, in the denominator, it says I minus 2. If you're going to use a complex conjugate, you got to make sure that it looks like this. Negative 2 plus I. So it's better to write it in that form so that when you apply the complex conjugate, you don't get the wrong thing. So it's going to be negative 2 minus I. So that's my hint for the complex conjugate in number 12. Complex conjugate. So you're going to be multiplying by that. Okay, so I just rewrote it so it could be in that proper form. And if you want to see the way it's written, complex conjugates looks like this. So a plus bi multiplied by a minus bi. So it's always that sign that is attached to the bi that's going to be flipped. So just be careful, because you don't want to end up with an incorrect expression, or an expression that isn't helpful in simplifying the rational expression. Okay. All right, so we got that.